Hello everyone. So in this video I just want to give you a very brief overview of how you can plot distributions in R. And specifically for this video, just because we haven't talked about continuous random variables yet, I'm just going to focus on a couple examples involving how to plot discrete probability distributions in R. So basically, if you think about a binomial random variable can take on a certain range of values from 0 to n, and we might be interested in plotting those values similar to how we were looking at how we could graph a probability distribution from a probability distribution table. How could we do that for a certain binomial random variable or a geometric random variable or any of the discrete random variables that we're going to be talking about? And so the reason I'm mentioning this is because if you look at the additional practice problems for the 2.3 and the 2.4 notes, there are actually a couple questions in here that ask you to plot PMFs, or more specifically, they ask you to look at the skewness of certain different binomial distributions in the case of 3.46. And I've tried to write out a little bit about the plot function here in the solutions, but I figured I'd make a video as well just to kind of explain it in a little bit more detail. So if you're going through the additional practice problems and you look at 3.46 or 3.47, hopefully this video will help you with that, and I've mentioned it here at the top of the 3.46 solutions. So I'm going to go ahead and use R here, and I'm actually going to refer to, let's start with a binomial example, just because that's a distribution that we talked about at the time that this video is going to be published. So let's actually look at the example on page 6. So let's look at example 2.4.2, and let's see if we can plot this particular binomial distribution. So in other words, what we're going to be doing here is we're going to be plotting all of the values that our random variable y can assume. Those are going to be on our x-axis, and on our y-axis we're going to plot the corresponding probabilities for each value of y. So for example, for y equals 20, this probability is going to be in our plot, as are the probabilities for y equals 0, y equals 1, y equals 2, etc. So I'm just going to put that to the side just so that we can reference that question. And let me go into RStudio. So again, you can do this whether you're using R or RStudio. If you're using RStudio, what's going to happen when you make a plot is it's actually going to show up in this window here. It's going to activate the plots window, and it's going to show the plot here. I'll do that in a second. If you're doing this in plain old R, it's just going to open up another window in the R console. So let me just open R here really quick. So you type your code in here, blah, 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 and if you hit enter, if it's a plot function, it's just going to open a plot window in this R window, and you can just close that without closing the console. Here you can leave the plot here, you can close it, you can actually export it pretty easily, you can zoom in on it pretty easily, but we'll talk about that in a second. So I'm going to make that as small as possible for now, then we'll take a look at it. All right, so what I want to do is I want to plot this particular binomial distribution. So a binomial distribution with an n of 25 and a probability of success of 0.66. And the way that I'm going to do that is I'm going to use the plot function in R. Now there's a lot of stuff the plot function can do. We're just going to kind of be using it at a very basic level. Like I said before, this is not an R course. We're not going to be going through all of the stuff R can do because it can do a lot. The plot function can do a lot, but we're really just going to use it to get things like this, just very rudimentary basic graphs, just so that you can see what a distribution shape looks like, or talk about its skew. So if you're familiar with R and you're familiar with the plot function, there's going to be a lot of stuff I'm leaving out of this function, but for our purposes, this is the extent that we would be using the plot function. So there's three things I want to put into this plot function, three arguments. I want to put in x coordinates, I want to put in y coordinates, and I want to put in the type of plot. And you can see in RStudio it actually gives you a little bit of information as you start typing these things in. But these are basically the three arguments: x coordinates, y coordinates, and the type of plot. So let's go ahead and start filling those in. So I'm going to start with the x coordinates. So what I mean by the x coordinates is I'm basically going to be plotting points in this plot. And what I want for my x coordinates, kind of like we talked about in the 2.2 notes, is I want the values that my random variable can assume along my x-axis. So y here, since it's this type of distribution, this binomial random variable, it can assume all values, all integer values, from 0 to n, 0 and n included. So my n in this case is 25. So for my x coordinates here, I'm going to put all the integers from 0 to 25, which I can do by typing 0 colon 25. So those are my x coordinates. Now for the corresponding y coordinates for each of those values of x, what I want to do is I want to plot the probability that y equals each of those values. So the probability that y equals 0, the probability that y equals 1, 2, 3, etc. And the neat way that I can do that in this plot function is I can actually put in the dbinom function. Remember the dbinom function, actually let me do this outside of the plot function first. Remember that the dbinom function gives you the probability that your random variable exactly equals whatever you put in here for your first argument. So like here in our notes, we wanted the probability that y equals 20, so we did dbinom 20, and then our n, and then our p. So if I just do the dbinom function here outside of the plot function, and I do from 0 to 25 for my x there, 25 as my size, my n, and 0.66 as my p, my probability of success, if I run this just outside of the plot function, what it's going to do, oops, sorry, it's giving me, ignore that, it's giving me an error because of this plot window. I'll talk about that in a second as well. But if we ignore that error, let me make that a little bit bigger here. Let me just do this one more time. Ignore that error for right now. What it's doing here is it's plotting all of the probabilities associated with these values of y. So here's the probability that y equals 0, y equals 1, etc. And since these are the things I want as my y coordinate, or my y coordinates in this plot, what I can do is I can actually put this whole thing, this whole function, as my y coordinate argument. So here's my x coordinates. The probabilities here are my y coordinates. And then to get a specific type of plot, we can tell our a couple different types or display versions. So what I'm going to do, and this is probably the easiest way to do this, or the easiest to read way of making a plot for a discrete distribution, is to make a plot like this, where for each value of your x variable or your y variable, you have a line that goes up to the corresponding probability. And in this plot function, I'm going to say for my type here, I'm going to say in single quotes h, lowercase h. And what that does, let me see if I can get that those directions to come back up here. There we go. So I can't move my mouse or this will go away, I think. But if you look at that information it's telling us that there's a couple different types of plots that you can make. So if you type in a P here for the type, you're going to get just the points for all of the x and y coordinates, so just the points there. L gives you lines, B gives you both. You could get a couple other things. The thing we want is H, which gives us those, like it says, histogram-like vertical lines. So I'm just going to go ahead and put in single quotes there, H. And this will give me a plot like the ones that we have in the key here for the additional practice. Now, one thing to note about doing this in RStudio is if you have this sidebar window too small, like I have here, and I try to run this plot function, it's going to give me a whole bunch of errors here because it's basically telling me that this region that I had here is too small to put a plot in. It's basically saying there's not enough room to put the plot. But if I expand that out, say to here, and I go ahead and try to run that, then the plot's going to show up. So if you try to run a plot in RStudio and it gives you some weird error, it just gives you a bunch of gibberish. Here it's fine because I've already run the plot. But if I were to clear this and try it again, it would give me an error. There we go. If you get something like that, it basically just means, as it's saying here, the plot's margins are too large to display. So it just wants you to expand that window out, and then your plot will appear. And so there is our plot of this particular binomial distribution with an n of 25, a probability of success of 0.66, and here are the corresponding bars for the values of y that give you the corresponding probabilities. Now this is pretty small. In RStudio you can click zoom and it will put it in a separate window. You can make that big if you want to. If you want to save this as something, you can click the export button You can just copy it to your clipboard if you want to. You can save it as an image if you want to. You can save it as a PDF even if you want to. You can do anything with this. You can even just take a screenshot of it and put it in a document if you wanted to. But it's just a nice quick way of getting a plot. In R, let me just do this in R so you can see what it looks like. So I'm just copying that and I'm putting it in R. So notice it just opens up a graphics window here. There's the plot. You can expand this and make it bigger if you want to. You can also right click and save it as something. You can even print it if you have a printer and you want to print it. These things you can copy and put in like a Word document or something if you want to. But it's the same sort of a thing. And you can just close this thing without messing with your console window. So that's an example of how to do a plot in R. Now, of course, we'll see this with continuous random variables later. I'll show you kind of a better type to work with when you're dealing with continuous random variables. But for now, let's do one more example, actually, just to show you a different distribution, since all of these ones in this key are binomial random variables. We haven't talked about this yet at the posting of this video, but I'm going to do one of these for a geometric random variable. Now, a geometric random variable, as we'll learn probably on Wednesday, so the 26th, a geometric random variable is basically a special case of a negative binomial random variable, and it's counting the number of trials until the first success. So it's the number of the trial on which the first success occurs. So we'll talk more about this on Wednesday, but when you talk about a geometric random variable, the random variable x can assume values 1, 2, 3, 4, etc. So the first trial is the first success. The second trial is the second success, or the second trial is the first success. The 80th trial is the first success, etc. So this is a little bit different than the binomial because with the binomial we have a fixed maximum for our variable's value. For a negative binomial random variable or a geometric random variable, you don't have that. And why I'm mentioning that and why I want to do an example with the geometric is because sometimes when you're plotting a random variable that doesn't have that nice maximum value for the random variable itself, where we're not bound by n or anything like that, you might have to mess around with the plot a little bit to make it actually cover most of the values that the random variable can assume. So we'll learn about the dgeom code in a little bit, but I just want to do this as kind of a quick demonstration of another plot. So this might be a good one to look at after we've done the 2.6 notes, just to see what this distribution is actually representing. But just to show you another example of a plot, let me look at this example 2.6.1 here. So here we're talking about a farmer gathering eggs, and the probability of any given egg being unusable, cracked or broken or whatever, is 0.08. And x is the number of the first egg that is unusable. So it's the first egg we run into after we start maybe gathering them that is cracked or broken or whatever. So maybe I want to plot this distribution of x, the distribution of the trial of the first success. In this case, the trial, the egg, that's the first unusable egg. So I'm going to go, once again, do plot here. Now, again, we'll see this a little bit more on Wednesday, most likely. But the way that you enter your x here for the dgeom function here is you do the number of trials of interest minus 1. So what I mean by that is the smallest that a geometric random variable can be is 1. And so the smallest this x value you can have here is 1 minus 1, or 0. So my smallest geometric random variable value here is 0. But there is no maximum, because I could technically have the first success on the 10th trial, on the 80th trial, on the 500th trial. It becomes less and less likely that that's going to take that many times to get the first success, but they're all still valid values for the geometric random variable. So for my first plot here, I'm just going to guess, and I'm going to use 40 and see what that looks like. And if I need to adjust this, I can after I look at my plot. We'll kind of see what that means in a second. And then I'm going to use the dgeom function. This takes on my values of x, so I'm going to match that with my x-axis here of 0 to 40. And it takes my probability of success. There is no n for the geometric distribution, so I just need to put in my probability of success, which is 0.08. And I'm going to again make this a type H plot to have those nice lines that we're working with. And I'm getting an error because I'm missing a parentheses. There we go. All right, so let me see what this plot looks like. So there's my previous one. Let's look at this one. So this one looks like this. So you can see that I have a higher probability of observing my first success on some of these lower numbers of trials, and that probability of success of the first success starts to taper off as we get higher and higher with the number of trials. And it looks like I still have some relatively, well, they're not large probabilities, but I have some probabilities here that looks like they could extend beyond 40. So let me just do 100 and see what that looks like. Here I'm just messing around because I don't know what this distribution looks like. I don't know how far or how many trials I'll still have a relatively reasonable non-zero probability to work with. So let's just replot this and take a look at it. There we go. Okay, now we're starting to get really, really tiny probabilities there. So this might be a good graph to stop at as far as the quote-unquote maximum value of my random variable, because if I keep going beyond this, I'm just going to start seeing that tail go off further and further and further, and it won't be as interesting. So it looks like maybe 100, maybe even less than that, maybe 80, but let's look at the 100. That looks like it might be a good representation of the general picture of this random variable. The negative binomial has the same issue where there's not a maximum value for your random variable. Same thing with Poisson when we get to it. So if you're ever making graphs like this for practice or whatever, you may need to mess around with your x-axis a little bit, or the maximum value your random variable can assume, just so that you can get a graph that looks like it encompasses most of the plausible or significantly non-zero probability values of x or your random variable that you might want to look at. But I just wanted to do this one as another example, just showing you that for some of these random variables, like the geometric or the negative binomial, you might need to mess with that x-axis a little bit to get the full picture of what the distribution looks like. And like I said, I will make another one of these videos when we get to continuous random variables in probably another week or so.